Okay, so here we're going to talk about the Arrhenius equation, and we can use this to determine the activation energy for a reaction. So first of all, just need to cast your mind back to this thing here, okay, what am I drawing there? I'm sure you realize it is the Boltzmann curve, and this is the energy, and this is the number of particles, okay? Right, now, let's just say that's a certain energy there. Let's call that EA, which stands for activation energy. Right, now, I don't know why, but mathematically, the fraction of molecules with energy greater than EA is given by E, which is a mathematical constant, about 2.71 or something, to the power of minus EA, so that's the energy we're talking about, R, which is the gas constant, and T is absolute temperature. So don't forget the gas constant measures joules per mole per Kelvin, so that's going to mean that our answer at the end for activation energy is going to come out in joules, not kilojoules. T is the absolute temperature. So that's the proportion of molecules with energy greater than EA. It kind of follows on from that, well, let's just write down the rate equation. We've got rate is equal to A to the X, B to the Y, etc. So that means if you keep the concentrations the same, don't mess about with the concentrations, and you only change the temperature, okay, only changing T, then rate is proportional to the rate constant. And we can kind of interchangeably use those. You'll see a bit later. Right, so what we can say is that rate is proportional to the number of molecules with enough energy to react, which is given by that. So we can get rid of that sign, proportional sign, and replace it with a constant. So we can get rate is equal to A to the power of E minus EA over RT. Now, in all the past papers they've ever given, they always give you this equation. You don't have to memorize it, but I think you probably should memorize it anyway. And that is the Arrhenius equation. As I say, rate and rate constant are interchangeable, so it's also, you can change that. The value of the constant will change, but you can also say that's true as well. Right, so if you do maths, then you probably find this easy. If you don't, don't worry, just learn it. But if you take logs of both sides of the equation, you're going to get ln, natural log, which is log to the base of this number E. Okay, ln K is equal to ln A minus, and the E disappears, isn't it? EA over RT. And I'm just going to rewrite that a little bit like this. Multiplied by 1 over T. And then I'm going to linearize that, so I'll make it fit into our Y is equal to mx plus C. So Y is equal to mx plus C. Right, the intercept is this ln A, the log of the constant, and we're not really interested in that, so we can kind of forget about that. We're on the y-axis. If we plot ln K, yeah, or it's okay, this can actually be ln rate as well, because I said rate and K are proportional to each other. So ln rate is quite often what you do plot. And then what's changing? Well, we've got X, which is this 1 over the absolute temperature. So that means our gradient is this thing here, minus EA over R. So the gradient minus the activation energy over R. So let's draw a little, let's plot a graph then. So you do a series of experiments at different temperatures. So you've got rate, and you've got the temperature, the absolute temperature. The rate often will be, it will actually be 1 over the time taken for the reaction. You know, we're doing the iodine clock experiment, 1 over the time taken for the flask to go black, or if you did the disappearing cross experiment, 1 over the time taken for the to go so cloudy you can't see the cross. So that would be that. T is the absolute temperature. That's going to be in kelvins, isn't it? And then we're going to do, we need to do a little bit of calculations. So we need to work out Lun rate from our rate there, and we need to work out 1 over T. And that's going to give us pretty awkward numbers because it's going to be like 1 over 273. So it's always like lots of decimals and stuff, and it's quite easy to make a mistake. So then once you've done that, you get your axes, and you're going to plot 1 over the absolute temperature there, and you're going to plot Lun rate here, and you should get a graph with a negative gradient. Okay, because obviously, you know, as the temperature gets bigger, the rate's going to be faster. So as 1 over the temperature gets smaller, the rate's going to be faster. So you've got a negative gradient. Then once you've plotted that, and again, you really do have to be careful because very often these Lun rates are negative numbers. So you have to make sure that, you know, your scale is the right way up, and you remember that like -4 is actually bigger than -5, not the other way around. And these are always, you know, what is 1 over 273? What is it? 1 divided by, or 298 Kelvin 25. That is 3.35 times 10 to the -3. So when temperature is equal to 298 Kelvin, 1 over T is equal to 3.35 times 10 to the -3. So it's not very convenient numbers you're plotting along the bottom there. It's all really awkward numbers. So be careful. And then you need to determine the gradient. So the change in the y over the change in the x. So you work out your gradient, which is going to be a negative value by looking at that. And you know, we worked out that before, that is equal to EA over R, minus EA over R, sorry. And then so to work out the EA is equal to minus the value of the gradient times the value of R, which is 8.31. And that is going to give us an answer in joules, because this is joules per mole per Kelvin. So you probably want to convert that to kilojoules. Most of the time when I've done that disappearing cross experiment, so just the disappearing cross experiment, just to remind you, is when you get thiosulfate and you add acid to it and you get sulfur solid, that makes it go cloudy, and that's your disappearing cross bit, and you get SO2 gas and you get H2O. Usually when you do this experiment, you get a value of the activation energy approximately equal to -30 kilojoules per mole. Okay, so do be really careful doing that Arrhenius equation. It's just the numbers on these scales do tend to be very awkward to plot. Okay, we'll leave it there.